Brief review of conic sections. Review this. Don't understand everything I say. Watch this again. Say it kind of quickly. And even if you think you got it, I'm going to say it quickly enough. It shouldn't take you long to go through it and make sure you understand every nuance. Okay. So. First thing is. Ellipses and hyperbola are constructed using rectangles, not software, not nothing else. Unless if you want to really accurate. Okay, you don't rely on software. There's a rectangle. That's supposed to be the center of the rectangle. An ellipse is going to be tangent to the rectangle here, 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 and here. So we make a tangent here. We do our best to come down and make a tangent here. Try to make a tangent here. Of course, it's impossible to do that perfectly and get a perfectly. Whoa, that's really imperfect. You got it. Okay. Okay. Hyperbola. Got these lines through the diagonal lines. Extended beyond the ellipse, because hyperbolas are outside of the extended beyond the rectangle, because hyperbolas live outside the rectangle. Okay. So I'm going to have two different hyperbolas here. So they're tangent at the points. Okay, now one of the hyperbolas is going to be tangent at this point. And it's going to be asymptotic to these lines. And of course, we have the same thing over here. Let's see if I look out and get this one right. Yeah, I kind of missed it. And it was a little low, but you get the idea. Okay. The other one. Here. I'm not going to get into the terminology. I'm going to define the terminology. I just hope you'll read it. But these points are called vertices. It's like the vertex of a parabola. Hyperbola looks kind of like a parabola, but the parabola keeps getting steeper and steeper. Hyperbola steepness levels off. It's asymptotic to a straight line. Okay. Got it? Okay, well, that's fairly straightforward. Make sure you understand every bit of that, though. Okay, now to construct it. For an ellipse, x squared over a squared plus y squared over b squared equals 1. Hyperbola x squared minus y squared x squared over a squared minus y squared over b squared equals 1. Okay. And that's going to turn out to open horizontally. That opens vertically, it's y squared over b squared minus x squared over a squared equals 1. provided the center is at the origin. Okay. If the center isn't at the origin, center's at HK, you just replace X by X minus H, replace Y by Y minus K, just the way you shift graphs horizontally and vertically. In pre-calculus, you learned it in pre-calculus, if you learned pre-calculus, you probably did. Okay. If you didn't, learn it. Okay. And you're gonna need it. All right. Make sense? Now I can label. Here's the x-axis. There's a y-axis. Okay. Here's the point. Zero A. Here's a point, zero negative A. Just to check, make sure I've got the things opening in the right direction because I'm famous for doing things backwards. I always check myself, which means you see me do a lot of corrections. Okay, and I have to do a correction. I've got these colors up here. It's going to be a well pain in the butt. So I don't want to do the corrections, but let's see if I do it right. Okay. So if y is 0 and x equals a, does this work? Well, if x is a, you got a squared over a squared, that's 1. And y better be 0, so you got 1. Oh, okay. And what do you think the points are going to be here? Well, I bet you can guess them. 0, negative b. And I didn't leave myself a lot of room to label this, but 0b up here. Okay. That's it. Now there's actually a lot more to what you can do with conic sections. I'm not going to write down how you translate them and ship them and stuff. Okay, read your text. Read any introduction to conic sections. Anything on the web. It's half decent. Tell you the same stuff. Okay. Most of the time they don't show you this rectangle, but that rectangle is really handy, especially if you want to get a decent sketch. And for the purposes of what we're going to do in this course, quadratic surface can be seen as a stack of ellipses that either grow, or ellipses, hyperbolas, and parabolas. I didn't mention parabolas. Probably do that real quickly. Okay. Parabolas is like a y equals x squared. You got to direct, but you got to focus. You got to vertex, all that stuff. Okay. And I expect that you've seen that. If you haven't, you want to read it. Okay. So I'm going to assume you know how to do parabolas. For ellipses and hyperbolas, which are what give you some of the more complicated quadratic surfaces. We can think of a stack of growing rectangles. And then we just, at each level, we sketch in whatever the quadrant, whatever the conic section is. Okay. If you know how to do that, it helps make sense with the pictures. And helps you see how to construct these things. And of course, what we're doing is we're moving into 3 dimensions. You got to move this stuff into 3 dimensions. So you can imagine if I just took the orange hyperbola and said, okay, the next one coming out toward you is going to be 10% bigger, 10% scale, 10% bigger scale, 110% size. So you're going to have hyperbola, then a bigger one, then a bigger one, and a bigger one. Come out like this. Whether you understand that or not, it's the kind of thing you want to understand here in another week or so. Okay. Okay, I said some stuff there. That didn't get recorded. But talked about how quadratic surfaces, that probably got recorded, can be seen as stacks of these things, like where the orange hyperbola, you do a stack of orange hyperbolas with bigger and bigger rectangles of the same shape and you get something that comes out like this, called a hyperboloid of two sheets. Okay, so there are different things. I might have already said that, I don't need to say too much more about it because you're gonna learn it. Okay. So a circle is just an ellipse in a square. A equals B. So you get x squared plus y squared equals r squared. And that's of this form, because you can divide through by r, you get x squared over r squared plus y squared over r squared equals 1. Got to do the algebra manipulator, but it's not difficult. Okay. So there's a circle. Sphere, x squared plus y squared plus z squared equals r squared. That's in 3 dimensions. Centered at the origin in this case. If you want x minus h squared plus y minus k squared plus z minus p squared equals r squared, then the center would be at hkp. Okay. You go to 4 dimensions, you get the 4 sphere. It's one of the most complicated things anybody has ever tried to analyze. You can't visualize it. Mathematics is just beyond difficult. People finally understood something about the 4 sphere that nobody's understood ever within the last 10, 12 years. Huge result. I don't understand. I'm not an algebraic topologist. Okay. Yeah, far from it. Okay. Now, other things, unit vector in the direction of vector v is v over its magnitude. You're just dividing an arrow by its length, which gives it a length of 1, which makes it a unit vector. Okay. It defines a direction in space or in the plane if you're in 2 dimensions. And you can understand a lot by 2 dimensions, extending it to 3. Extend it to 4 and things get weird. But most of the extensions are straightforward. Okay. Stuff that an engineer would use. Most engineers. Okay. Okay. Quantum engineer might be, I really want to think about that. Okay. That's easy. Define the dot product last time, simple. Okay. Might define the cross product today, but probably won't have time. It'll come up next week. Takes a little motivation, a little bit of stuff to do. Okay, but we've got the dot product. Okay, these are orthogonal to W if V dot W equals 0. And also neither one of these can be 0 vector. Okay, so non-zero vectors be orthogonal if and only if the dot product is 0. Because if the dot product is 0, the dot product is equal to the product of magnitudes. And if the other vector is 0, that product isn't 0. Times the cosine of theta, which means cosine of theta is 0, which means they're in 3 dimensions, it'd be perpendicular, or in 2 dimensions. Okay. In 4 dimensions, you can't really say perpendicular because that gets weird. We say orthogonal. And in general linear algebra, we use the word orthogonal, but it's a generalization of perpendicular. And it's a generalization of dot product of 0. Okay. So that's very important to understand. Got to keep looking at my list. See what else is here. Yeah, okay, I'm going to pause for a second. I got to make a decision. You got a triangle. You got the coordinates of the 3 points in the triangle. Then if you know the coordinates, you can find vectors. And you've already done vectors, you know, the vector A, B. So you have here A, you have here B, you have here C, you have here the vector A, B, the vector B, C, and the vector A, C. Incidentally, AC equals AB plus BC, right? Make sure you understand why. Should be totally obvious, but you know, depends on how much you do when you came in, whether it's all same thing or not. Okay, AC equals AB plus BC vectors. All these angles, alpha, beta, and gamma. If you know the coordinates of these 3 points, then you can find the vector AB and the vector AC, and you do the dot product and figure out what alpha is, right? Well, I'll write it out for you. Okay, this dot product is length of this one, which is the length of the side, right? Multiply by cosine of alpha. So if you got the coordinates, you can do the dot product and find the lengths of the sides, and you can solve for alpha. And similar for beta and gamma. It's kind of a neat idea. Not too difficult. Okay. Big deal. Got a vector B and a vector W. B can be expressed as a sum of 2 vectors. Let me label B out here. Okay. Sum of 2 vectors at right angles. 2 vectors would be I'll call them B parallel. That's not an 11, that's a parallel symbol. And B perpendicular, which will be here. Now you know enough that the sum of these B got equal to. Okay. How do you calculate B parallel? If I take this triangle here, this side has magnitude B. This side has this angle theta, has magnitude equal to the magnitude of B times the cosine of theta, doesn't it? And you should be able to look at a triangle and just naturally see exactly. That's cosine, that's a sine. B times cosine, B times sine. Okay. If you got to think opposite, hypothesis, all that stuff, go ahead. But it should become natural to your eye. You're going to be an engineer. And it probably already is. Okay. So we have this, and conveniently, magnitude of B cosine theta is what? Magnitude of B, magnitude of W cosine theta divided by what? Show me a letter with your fingers. What would you divide by this by to get this? Yeah. Divide by the magnitude of W, right? Your eye knows that. Okay, if you didn't see it. Okay. And of course, what's this equal to? It's equal to, there's a gesture you can make that would indicate what it is. The gesture would be like dot product, right? This is the dot product. Okay. That's the scalar projection. Now, when I say the length of this thing is this, not really necessarily true, because theta might be greater than 90 degrees. If you look at the unit circle, as soon as you get past 90 degrees, that cosine is going to be negative, isn't it? Okay, so we call this the scalar projection. You're going to see this, I think, in homework coming up real soon. It's a scalar projection of V onto W. I'm not going to write of V onto W, but I'm going to write it this way. Projection onto W of the vector V. You're projecting the vector V onto W. Okay. Now that's not the vector V parallel. The vector V parallel has the direction of W, right? So if I know what the scalar projection is, and I know the vector W, how do I get a vector whose magnitude that has a scalar projection that has a direction of W? Well, I just wrote down here that unit vector defines direction in space. You put that idea together with what you need here. V parallel multiplied by W over its magnitude, that puts it in the direction of W. Also takes care of the possibility that this angle is obtuse, because then the scalar projection would be negative, because cosine theta is going to be greater than 90 degrees. Okay. And puts it in the direction opposite W, which is where it better be. Okay. I'll make sure you digest that statement, make sure you understand it. Okay, that's the idea. And of course, there's a formula, and engineers have a good way of forgetting the idea and memorizing the formula or using the software. Okay, it's not necessarily to your advantage to do that. It could be to your advantage to understand basic principle, which makes it way easier to remember things, less to memorize. So make your own decision. I think you're better off if you don't use formulas you don't understand until it's really necessary. This thing go really deep. I mean, eventually you're going to get to the limit of what you can handle. And then you got to know that the formula works. Okay. It's on the part it's just really complicated. They're empirical. There's no way to derive from principles. So you use your judgment, but in the stuff we're studying in this course, everything comes out from basic principles. Think about that. Okay, so V parallel, that equals the scalar projection times this, of course, the scalar projection is this. Which is V dot W over magnitude of W divided by magnitude of W. Times, never mind, that was really dumb. At least I understand the principle well enough to recognize that before I go too far. But all right. Okay. Times W over the magnitude of W, as I know, because it just put it down. I was focusing on something. Okay, now this is the way I write the formula. Okay, because I'm trying to write the formula in such a way that it means something. And the meaning is clear. Scalar projection, length of this, but maybe negative. Okay, just this triangle, this comes right out of the triangle, right out of the definition of the dot product and everything else. And then multiplied by the unit vector in the direction of W. Okay, that's what it means. That's how you do it. That's the total explanation of everything I did here. Now, if you just want a formula that people can memorize and use without understanding, which I don't think is a good idea at all, because projections are so important, and understanding these relationships is fundamental. You write it this way. Which is the way I would design times W. I would write it this way if I was trying to teach people who are never going to understand any of this anyway. So hopefully they can use it if they learn how. Okay? I don't like that. I don't like this formula. If you don't see this inside this formula, you don't see any of this. And if all you got is this, there's no reason. If you can answer the question somebody's asking you using this without understanding anything, great, but you don't understand anything. You're an engineer, you're not as good an engineer. Okay. And you're not going to see relationships and understand relationships that you might need to understand, depending on kind of engineering you do. Okay, well, end of my lecture on stupid ways to write things. Bit obscure. Made it. Now, of course, if you're writing it for people who understand this, I think most of you do. You say, here it is, you see this inside of it, that's what it means. It's not a way of approaching the formula, but you don't just give them the formula. Okay. Now, in engineering, sometimes you got to do that. There are too many formulas, or too much. Okay, so I'm not criticizing engineering at education. My grandson's just been through 93% of it. Okay, at Tech. And I know the shortcuts they have to take. He's going to be much better at designing the power system for nuclear plant than I'd ever be. I don't even have the patience to memorize a bunch of stuff I don't totally understand. Okay. I think I would understand most of it. There are details. You've got to take shortcuts to be able to do this. And nobody's going to be asking him to design the power system, running power plant until it's had 10 years of experience. And proves himself to be good enough to do that. To give him small project, just like they will you in engineering. Start expanding your abilities. You don't really learn engineering until after you graduate. Okay. And you ask Brian Hale. And he's an engineer, I'm not. He said, oh, I'm full of it. Well, okay. But math course, we learn the math. Okay, so projections are a big deal. I wouldn't have spent that much time on it when we got a lot of stuff to talk about. Something I want to emphasize. You'll see in the next few weeks. Okay, go to box. Ignore the flaps. The x-axis is parallel to this side, y-axis on the side, z-axis vertical. Then this thing's about, so 9 inches by 12 inches by 7 inches. Okay. So a diagonal from this corner up to this corner. Okay, diagonal that goes from, I don't know how to handle this camera, this corner to this corner, okay? Gonna be like 7i plus 12j plus 5k. The vector from one corner to the other. Okay. Won't still be in my way, but the vector from corner to corner makes some angle with the x-axis. Okay, the cosine of that angle is what we call the direction cosine. Makes an angle with this axis, makes an angle with this axis. Cosines of those angles are the direction cosines, and they're simple dot products that you can learn about. I'm not going to go over. I don't want to take the time to write it out. And the angles, of course, are the inverse cosines of the direction cosines, right? So you could define a direction in space by the direction cosines. You could define that vector by the 3 direction cosines and its length. In fact, you only need 2 direction cosines because the direction cosines, you have their square, that up to something new. Okay, so that's the importance of direction cosines. They can be really handy, especially in a lot of engineering and statics and stuff. You ever seen them in statics? Just shake your head yes or no, don't say anything. Recording's on. Okay, yeah, maybe not. Not sure. Not sure how important, how much they're emphasized if everything's being done by software. Okay. And again, I don't object to everything being done by software, but statics, of course. There's a guy I find a little offensive, but engineers and mathematicians always find each other a little bit offensive. We love each other. Okay. You know, 80% of my fraternity brothers were engineers. We got along. Okay, we just approach things a little differently. They thought I knew something. I thought they knew something. They're both kind of right. Okay. Okay, I got to look at my list again. Okay. So, here's once more. Okay, a little bit about parameterization. Board trades. Okay, so let's say that y equals 2 squared, x equals 2 cubed. Let's say this equals 0 to 1. Okay. Well, when t equals 0, y is 0 and x is 0, right? So of course, you get the point 0, 0. When t is 1 and x is 1, well, we get 1. Both points. Between equals 0 and t equals 1, we don't get points on the straight line. Okay. Now, if it's y equals t and x equals t, y would equal x, and y equals x is a straight line. Okay. But now y is t squared, x is t cubed. Okay, what's bigger, t squared or t cubed? Just say x or y. Okay, it's 3-to-1 x. And that's wrong because t is between 0 and 1, and the cube of the number between 0 and 1 is smaller in the square. I think 1/2 squared is 1/4, 1/2 cubed is 1/8. Every time you multiply by a number smaller than 1, your result gets smaller. Okay, so I kind of want to keep that in mind. Now, as soon as t is bigger than 1, yeah, t cubed starts dominating. Should be well. If you want to think about it. So, okay, so anyhow, that means your x is going to be less than y all the way from here to here. Okay. And if x is less than y, then your curve is going to have to look like this. That's not what I'm going with. Maybe something like that. It's going to have that kind of concavity. Because at every point here, I mean, here's where x equals y. Okay. At this point, y is clearly bigger than x, right? Okay. Now, shape of the curve and x and y. Okay, that's really characterize what I'm doing here, but eliminate t. Okay. Here's a cube root of x. Y is a cube root of x squared. That's equal to x to the 2/3. Take the derivative if you want to find the slope. Okay. Analyze the curve using whatever you need to analyze. It's fairly simple curve analysis. Fairly simple. You know, you got derivatives and second derivatives and all that stuff, and maybe that's the path. And you got something moving along the path, you want to find its velocities and accelerations and all that stuff. Okay. So there's a lot of reasons to have this perspective. Okay. Well, that's good, but let's say we don't want to go to this trouble, but we want to find dy dx in terms of t. In other words, if t is time and you're moving along this and t is, let's say, in seconds or whatever, this is a 1 second path. Okay. You're speeding up, you're slowing down, what's your acceleration up and down? And what's your direction at a given time? You can find that direction if you know what time corresponds to a point you're looking at and so forth. That's not a good statement. Okay, if we want to find this just in terms of t, it's dy dt divided by dx dt. You kind of think of it as a fraction, or your dt's cancel out. You get dy dx, which is the direction, okay? Or the slope, okay? and the slope is directly related to the slope direction. Now, what really you can think of is dy dt is how fast you're moving in the y direction. And dx dt is how fast you're moving in the x direction. So at any point, you got some velocity in this direction, some velocity in this direction. The resultant velocity is in your direction of motion. Okay. And you have that slope. Well, it's worth thinking about. And that's a little bit of a hand-waving explanation, so don't take it too literally. It gives you the idea. Okay. Well, pretty simple ideas here. You have a parameterization of a curve. This would be a parameterization of, y curve. Okay. So parameterization of the y equals x to the 2/3 curve. Then you can figure out the slope at any point directly from the parameterization. Okay. Or directly from the function. You can get the function from the parameterization or the parameterization from the function. And that's all stuff that's supposed to be part of calculus 1, calculus 2. Depending where you had it and when, maybe it was, maybe it wasn't. Okay. You want to review it, or you want to look at it. It's in chapter 11. But those are kind of two of the big points. Also, maybe we saw parameterizations yesterday. Okay, let's do another parameterization. Let's do let's think about that one for a minute. Talk about it a little bit. Okay, just reminding you something we did that last time. This is a parameterization of the unit circle. Okay. Well, no, it's similar to the parameterization of the unit circle. Parameterization of the unit circle. X equals a cosine of something, y equals a sine of something. It doesn't even have to be t, it could be t squared or 2 pi t, whatever. Okay. But parameterization of the unit circle is this, which means that we have circle, right? And what happens if we put an a in front of x and a b in front of y? Your x's get a times bigger, your y's get b times bigger. Of course, a is smaller, a times bigger is actually smaller. But, language isn't real good at modeling that, okay? So this okay. So here's a, here's a, here's b, here's b. And now you distort the circle. You stretch it this way, you stretch it this way. And what do you get? What letter does it start with? Give me letters. So we're just doing what I showed you to do. Okay, now what happens if you eliminate t? Divide by A, do the inverse cosine, you get these inverse cosine of X over A. So Y equals B times the sine of the inverse cosine of A, X over A. So what's the inverse cosine of X over A? You have to draw a picture. Hypotenuse 1, adjacent side X over A. And this angle here, which I don't have room to label in there, but that angle is the inverse cosine of X over A, isn't it? Okay, so what's the sine of that angle? I know that angle is the side of the triangle. So Y equals B times should have been square root. Parentheses in there. Pythagorean theorem. This side is the square root of 1 squared minus this side squared, right? Because this square plus this square equals 1 and all that. And that needs to be secondary stuff. Okay. So we have this, right? So get it over here. Y squared equals B squared times 1 minus X squared over A squared. Well, I'm just gonna rearrange this. It's all I'm going to go through all the steps. Get the equation of the ellipse. Started out with. Okay, now to get that, you divide both sides by B squared. The B squared goes away here, it appears here. Then you add the X squared over A squared to both sides, which is real simple. Really. And of course, you probably want to put the X squared over A squared first, because that's the way it's usually written. Now, okay. Make sense? Well, moving along, we've got some time left. Getting more done than I thought. And start to run through it, so I'm going to kind of press things. Okay. R equals cosine theta. R is the distance from the origin. Well, there's terminology that goes with this. If I've got a point out here, okay, that point is characterized by R. How long this arrow has to be. And of course, we're familiar with R vectors last time. And the angle theta. Okay. So Theta of R and theta, what I said. Now they didn't write out everything I need to write out. Make sure you understand their words. Okay, so now we can make theta. Okay. Theta, we'll let go from 0 to pi. Then the cosine of theta, well, cosine of 1 is 0 is 1, cosine of pi over 4 is approximately 0.7. Pi over 2 is 0, approximately negative 0.7, and negative 1. I'm eating up a lot of boards before I hope I have something here. I can always block the board, it takes a while to dry everything. Okay. And got some extraneous stuff that's been picked up here, so just quickly. Let's get some of that out. As clear as possible. Now we can go. Okay, so we're gonna plot this out. Okay. Theta equals 0, R equals 1. Length of this vector is 1. The angle it makes with the positive x-axis is 0. Okay. Then, and I was in an unfortunate place to label it. Theta equals pi over 4. R is 0.7. Well, if that's 1, then 0.7 be about here. Then theta equals pi over 2, R equals 0. Let me label these points. This point is 0. Sorry. 1, 0. This point is about 0.7 pi over 4. This point is 0 pi over 2. Just a different way of specifying points. Not particularly difficult, but some aspects sort of are. Then we've got 3/4, negative 3/4 pi, negative 0.7. Okay. Now 3/4 pi is out here. Theta is 3 pi over 4. But we've got to go negative 0.7 units in the direction of 3 pi over 4. Well, 3 pi over 4 is in this direction, but negative 0.7 units is back here. Okay, so that's a little short. It's not quite well done, but theta. That gets you around to this point. Well, you can work out the details and easily enough prove that if you keep going, well, if you go all the way up to pi, that your pi negative 1, pi is out in this direction, but negative 1's back here, so you're back at this point. This whole thing takes you around, and it turns out this is a circle of radius 1/2, centered at 0, 1/2, 1/2, 0. Okay. Just an example. How you could sketch a curve. If I want to find the area of that circle, of course, I already know the area is pi r squared, which is going to be pi over 4. I do an interval. And so here we got it again. Okay, put it inside a rectangle. Okay, so if this is the curve, how am I going to calculate its area using an interval? Now I could convert to rectangular coordinates. Just x minus 1/2 squared plus y squared equals 1/4. Okay, but that's cheap. You know how to do that, and you know how to do this. Well, what we do is we now divide theta. We divide this thing up into theta increments. We take the typical theta increment. Well, I'm going to enlarge it a little bit so I can label it. It's not the arc of the circle centered at this point. The arc of the circle centered at this point, so it's going to be narrower here than it is here. Or this distance is going to be a little less than this distance. This is some angle theta between this angle and this angle. What are the dimensions of this thing? So we've got that, and we've got a delta theta. Okay, so this is one theta, this is next theta. We've got a delta theta. We've got some theta in between, that's our theta star. I'll just say that's in between because I don't have time. Okay. Well, this distance here then has to be what? Okay. What do you think? Talk about it for 30 seconds or so. We partition the theta interval from 0 to pi. That gives us a bunch of thetas from 0 to pi. Okay. Then this corresponds to one interval of the partition. There's a delta theta, whatever the difference between your partition numbers are, is and you have R equals cosine of theta star. Okay. What's the area of this thing? Well, if you have a small partition, this thing is pretty close to a triangle, isn't it? Okay. Pretty close to a triangle. And that triangle would be half of a rectangle. If you put another one upside down on top of this one, that rectangle would have what dimensions? Okay. This is R. This is R. It's not exactly R because R, no, it's not exactly R star. Call that R star. Both this R and this R are close to R star. So if we put one of these here and upside down on top of it, we have a parallelogram. If our increment is really small, pretty much a rectangle. So the area is what? Well, first we've got to find how long this side is. Well, this is delta theta. So this is our delta theta by definition of the radius. So this area is R delta theta. Said that wrong. It's R delta theta times R. Okay, so this area now is close to them. Cosine squared theta delta theta. So you integrate zero to pi, because your partition the interval from 0 to pi, cosine squared theta would be theta. Okay. Now that's not very handy for the area of a circle because you already know the formula, but what if for the ellipse? Okay. You know, change some of the quantities in the parameter, or what if it's a spiral? R equals theta. Okay. Or what if it's a more complicated figure that you see if you read the chapter? And pull it, which section in chapter 11 and pull it coordinates. Okay. This method of partitioning your angle, giving you wedges, and then carefully writing out the dimensions of those wedges to obtain what you add up to get the approximate area. Take a limit as delta thetas go to 0. Get the total area. And that's going to be a very important process coming up. We're not doing integration yet, but I'm trying to give you a broad picture of polar coordinates. Okay, much more to it. So check out the chapter. Okay.